Hi everyone, my name is Debras. I'm a researcher in Toulouse in France. And in this presentation, I will talk to you about the models we've made with Gilles Chabrier on the interior of Jupiter in the context of Juno and Galileo, and how they seem to show a signature of a decoupling between the atmosphere and the interior. So this talk will be in three parts. We'll first show what our models rely on, before detailing the model physically speaking, and then showing what they imply both for Jupiter and for giant planets in general. Okay, so the first constraint is that we have to reproduce the Galileo's observation. That is that the atmospheric heavy element content is supersolar, and the observation by the microwave instrument of Juno seem to be in line with this observation. So there's a word of caution on the work of Tristan Guillot and the Mushball that seems to show that there might be some other conclusion coming in the years to come, but so far it seems to be quite a safe conclusion. So similarly, we assume that convection starts at 1 bar and 165 Kelvin. And again, with the work on the Mushball and the storms in Jupiter, it seems that the convection starts a bit deeper and a bit hotter, but we have verified that it doesn't change the conclusion of our models. So the more gravitational moments we use are the values calculated by Juno, observed by Juno. We impose that the helium content in Jupiter must be protosolar, so Jupiter formed in the protosolar nebula. The method we use is a concentric Maclaurin spheroid method, which decomposes Jupiter in spheroids of constant density. And finally, the value we obtain with this method are static values for the gravitational moments. And so we need to correct for the dynamically induced moments, so from the effect of winds. And we use a prescription of either Caspi et al. 2017 that were based on an exploration of the possible wind models, or of Caspi et al. 2018 that are based on the odd gravitational moments of Juno. So the equation of state we use is Chabrier-Masvé-Soubiran 2019. And so on this pressure density plots, what you see in solid line is this new equation of state compared to SCVH, which was the equation of state mainly used before that. And you see that with the new experimental data, so the circle, the squares, the triangles, SCVH is now excluded and it does not validate the new experiments. We have to include non-ideal effect because Jupiter is quite cold, and so there's the mixing between hydrogen and helium, and at least some repulsion. We use the work of Mileder and Herbart 2013, and we verify that we have always less than, or almost always less than, 1% of error on the density on the other quantities between our work and their work. And to compare, there's other equation of state that do in the literature that do worse than what we do here. So for water and other heavy elements, we use either the equation derived by Adrien Licari, and for heavy element, the Dreisen equation of state. Okay, so what is the issue? So on this plot, you have the contribution function of the gravitational moment as a function of radius. And so what you see is that the higher the order of the gravitational moment, the more it is sensitive to the outer layers. So what Juno measured is that J6 to J10, so high order gravitational moments, have relatively low value compared to what was expected and observed before. So what that means is that the outer layers are not very dense and less dense than what we expected. On the other hand, Galileo and Juno seem to show that the atmosphere is enriched in heavy elements, and the new equation of state are denser in the megabar region and in the outer layers than the previous equation of state. So what that means is that we have two conclusions that are opposites, that goes in the wrong way compared to one another. So the real question we had to ask when we were doing our model is how to couple these two conclusions. And so this is what we came up with, and these are 4 to 5 layers model of Jupiter. So in the outer part, you have an outer convective layer with the composition observed by Galileo and constant specific entropy. Then you have a region of composition change, very probably characterized by semi-convection and maybe miscibility between hydrogen and helium. I will come back to that point. There is then an inner convective region that is probably responsible for the generation of the magnetic field. and a very extended diluted core. So the presence of a compact core at the bottom of Jupiter is not a necessity in our models. So the first thing is that we confirmed the presence of a diluted core that were intuited 30 years ago by Dave Stevenson, but confirmed with the first Juno data by Sean Wall in 2017. We also show that there's a need for a significant entropy increase in the megabar region, and we couldn't get rid of this aspect in our models. And this entropy increase is most probably associated with a decrease of heavy element content with depth. So what that means is that the inner convective region is less enriched in heavy element compared to the outer convective region. I will come back to that point as well. There is also a need for the density to be smaller than the isentropic model if you were to follow the composition of the outer adiabats, so given by the external condition. And this seems to be counterintuitive, but it can be justified physically speaking. And finally, we put a strong constraint on the maximum mass of the compact core, which must be less than 5 Earth masses in our models. And the total metal mass is comprised between 25 and 45 Earth masses, and we can't do really much better than that today. Okay, so I say there is a need for a strong entropy increase and a decrease of heavy element content. So how is this physically justified? So the first explanation is an immiscibility between helium and hydrogen. It's possible, but it's not necessarily favored by a quantum mechanical calculation. And the decrease in heavy element content will not be sufficient by immiscibility. There is also the possibility that hydrogen goes through a first order transition from molecular to metallic, but this seems to be really out of the game for Jupiter, and it's confirmed by every simulation today. So what we advocate is that there is a real need for semi-convection. So for inefficient convection that leads to a hotter temperature structure than real convection, and the possibility to increase the necessity to increase the molecular weight with depth. Just a word to say that this semi-convection could be triggered by immiscibility between hydrogen and helium, because on Earth, it's the case, there is some semi-convection triggered by immiscibility between different elements, but it's not a necessity. Another word about semi-convection, if in the condition of Jupiter, semi-convection condition writes this way. So basically your temperature gradient must be higher than the adiabatic temperature gradient, but not too high compared to the molecular weight gradient, or you will just end up in a diffusive region. This factor, alpha mu and alpha t, they just depend on your equation of state. For an ideal gas, they equal to 1. But Jupiter is not an ideal gas. And so if you plot this ratio as a function of pressure, you see that around 0.1 megabar to 1 or 10 megabar, this ratio gets of the order of 10 or even 15. And so what does show is that semi-convection is thermodynamically favored deeper than 0.1 megabar. So it's not a proof, but it goes in the good direction. Additionally, just a word about the work of Lecointe and Charrier 2012. The evaluation of, well, their work on semi-convection shows that the increase in entropy that we require in our model is coherent with the equations derived at the linear order for semi-convection. Again, not a proof, but it goes in the good direction to show that semi-convection could be the source of the entropy increase in the megabar region in Jupiter. So in summary, what we have in our models is that if you look at J4 and J10, so our model uses the constraint by Galileo, they use a new equation of state, and they have a physical explanation for the entropy increase. In any case, they are in agreement for the value of J4 and J10 with CASP 17 or CASP 18, but we have an issue for J6 and J8 if you take into account CASP 18. So what that means is that there is a range of winds in Jupiter that could conciliate our models with the gravitational moment of Juno and the dynamically induced gravitational moment, but not with the wind model derived by CASP et al. 2018. So the first explanation is that our models are wrong, which is of course a possibility. So something might be missing in our models. Another possibility is that the work of CASP 18 is based on the odd gravitational moment, so it doesn't take into account a possible north-south symmetric wind contribution. And finally, there is a growing work showing that the neglection of the dynamic self-gravity effect in the work by Caspi et al. Could be a first-order effect on the J6 and J8 moment. And so this is an issue we are exploring, but which could reconciliate our models with the wind profiles in Jupiter. Okay, so in terms of implications, the first one is that we have two distinct regions of convection separated by a semi-convection region. And so that could be the sign of two dynamo regions. And this was actually proposed completely independently by Morata in 2018, that there could be a deep dipolar dynamo and a shallow multipolar dynamo happening in Jupiter. And so I refer you to these works to more details. So in terms of metal decrease, what we said is that we need either immiscibility or semi-convection, but how can we get to such a large metal decrease? We advocate for a factor of 2 in the decrease of heavy element content. So the first one is if phase separation is very efficient. There is a region of the parameter space that would allow such a decrease, but this is very, very doubtful. And it seems that latest quantum mechanics calculations are not going in this direction. So we could also have the fact that layered convection in itself triggers a sharp decrease in metals, but we don't think it's a good explanation as well. And our preferred explanation is that the semi-convection occurred a long time ago in Jupiter history, and it decoupled the atmosphere and the interior of Jupiter. And if it happened sufficiently long ago, all the atmospheric accretion of small bodies of the solar system on the atmosphere never reached the interior of Jupiter. And what that means is that the atmosphere of Jupiter is enriched in heavy elements, but not the planet in its whole. And it's just due to accretion over a few billion years. And what we show in our model is that you just need something between 0.3 and 1.5 Earth masses, depending on your assumption of heavy elements, to explain the enrichment of Jupiter. So if that were to be true, it would lead to crucial consequences on the formation model that usually use the atmospheric condition to explain the formation of Jupiter and on our understanding in general of the evolution of Jupiter. So what about the diluted core? So there was a paper by Morata in 2017 that showed that if you have a spherical core surrounded by a huge convective region, it won't survive for the lifetime of Jupiter. But on the other hand, if you have a kind of a diluted region, you can have a survival, a long-term survival of the core, either fluid or solid. So this seems to be completely in line with our models. And so there is, of course, the question of whether convection has eroded the core, or if the core, eroded core has another source. And there is a paper by Lueta that showed that it could arise from a giant impact early in Jupiter history that distributed the heavy element content of the core in the planet. I will finish this talk by 2 words of caution. The first one is on the evolutionary models. So first, we don't know whether there is layered convection in Jupiter. We don't know how superadiabatic it is and how old it is. Regarding immiscibility, it's the same. We don't know the physics of immiscibility between helium and hydrogen, and notably the amount of latent heat, and we don't know the shape of the immiscibility diagram. So if there is immiscibility, we don't know much about it. Regarding the diluted and compact core, we don't know whether the compact core was diluted through time, which requires some gravitational energy to lift up the heavy element. And we don't know whether there is a demixing of heavy element, which would be another source of gravitational energy in Jupiter. And we don't even know if Jupiter has ever been fully convective, which is often an input of evolutionary models. And if you just take one of these uncertainty, which is the presence of layered convection, Leconte and Chabrier have shown that the effective temperature of Saturn, depending on the amount of layered convection that you use, is a very different function of time compared to the isentropic model, which is the black line. And so with just one of these assumptions, the evolutionary model are very different. So if we take all of the unknown in Jupiter, we basically don't know what happened in Jupiter, and evolutionary models must be taken with extreme care today given the level of uncertainty we have. And some of these effects will go opposite, and so could just oppose one another and explain why some simple model work, but it doesn't mean that we understand the evolution of Jupiter today. Second one of caution, if our models happen to be true, it means that the atmospheric composition is not easily linked with bulk composition. If there is a region that breaks convection, then you can just simply enrich the outer parts without touching to the inner part of a planet. And we know for sure that Jupiter and Saturn are not adiabatic, and that might have lasted for several giga years, which leads to a factor of 2 or 3 in the total metal mass, depending on your assumption. So again, with extrasolar planet, there is a lot we can do, but we have to be careful with oversimplification that assume simple convective materials. Okay, so my takeaway message is that the Juno data excluded the older model of Jupiter. And so we have to somewhat more complicated model of the planet with a need for a diluted core, an extended region of composition change, which is probably characterized by semi-convection. And this kind of model puts strong constraints on the core mass, which can be more than about 5 Earth masses. So in my opinion, the prospects are that the study of the oscillation of Jupiter is a necessary next step, because we need some new diagnostic to study the internal structure. And similarly, the understanding of how the magnetic field is generated will bring some new element in the future understanding of the interior of Jupiter. So on this, I thank you very much, and I wish you a good conference.